I'm Travis Ty Kevin 83 McGeehan. I'm a full stack developer at Gordon Food Service in the Eastern United States. And I'm also an administrator for the TaskBot team and an ambassador for the Task Videos website and a task author. So you're probably going to want to know, I just said task 3 times. What the heck is a task? Well, I can explain both what a task is and what our team does. Tasks are tool-assisted speedruns. Speedruns being people trying to beat video games as fast as possible. And the tool-assisted side being wrapping those speedruns with input viewers and ways of slowing the game down to frame by frame and being able to play it back over and over again to script the perfect sequence of inputs. And this is a very great technical undertaking. You have to do a lot of emulator development, but there's also development. And what I'm going to be talking here is more about the reproduction of the video side. So if you have all these emulators, you got to make sure that the output from the emulator is really crisp and kind of preserves faithfully the original game content. So the TaskBot team, we take these tool-assisted speedruns and we actually move them to being played back on original hardware, back from the emulators. We verify, we call it console verification, that the emulator is behaving exactly the way that the console did. It's like a player piano for those old consoles. So the TaskBot team takes those tasks and translates them to consoles. And we do showcases like this at MagFest and GDQ. And just a word of caution for what I'm going to be talking about in general. The discussion here is mostly going to be relevant to archival of that kind of retro video game footage that would come out from a presentation like that. And it's going to be tuned towards animated footage because of that. And it's going to be this discussion and the player will be less relevant for live filmed video, except when you're trying to transmit like viewable archive copies of such film. So there's like 5 problems I want to talk about in a background to kind of explain why we needed to build RGB scaler. The first one is chroma subsampling, and you can think of the word chroma just like the word color, and subsampling is just like lower amounts of color. So there's a thing called 420 chroma subsampling. Again, color reduction, and it's a technique in video compression where the color data is stored at a lower resolution than the entire video to take advantage of how the human eye works. And this is kind of harkening back to when you had black and white televisions. Black and white televisions had only black and white. They just had a brightness amount and not a color. And then when they had color TVs, they were like, we need some way of backwards compatibility with black and white television, so you can just send one signal out from all the cable companies and it would get the same effect on a black and white television and on a color television. So you ended up with this system where there were 3 components. There was a brightness component and then 2 color components that act as differences from the main brightness, and that allows you to reconstruct red, green, and blue the same way that you would if you sent actual red, green, and blue signals. And games didn't typically take advantage of this sort of like color reduction that was possible by formatting the video in this way until the GameCube era. So the color components of that signal would often be a lower resolution than the brightness component, and then that didn't happen with like the NES, SNES, and 64. It only happened in GameCube and later when things started to be more like modern video signaling. Then the second big problem is these are really small resolutions and they don't have square aspect ratios. So what I mean by this is you have on a original like NES, the resolution is 256 pixels by 240 pixels. But when you display NES footage, it's always going to be in a 4:3 aspect ratio, which would be as if you had 320 pixels wide, not 256. So when you're capturing the footage, you want to actually make sure you capture it at 256 by 240 and not the 320 that you would be displaying it at. Because if you do, then you'll get these weird edge artifacts between a bunch of pixels and it won't look sharp. And then when you blow up the footage to be on your modern display, it's going to look like it has all those artifacts in it. And this is a really big problem, especially because the most color accurate displays that exist these days, like the Alienware QD OLEDs or LG's C3 line, C2, those kind of color accurate displays are really, really high resolution. So you have to do upscaling. So you need to make sure the source footage is in a square aspect ratio so you can blow it up without artifacts, and then you can blow up the aspect ratio correction along the width in that second step. So there's a third problem of scaling for display presentation, because not only do you get to do that aspect ratio correction, but you have to like decide some way of upscaling the footage. And in browsers, almost all web browsers use a bilinear scaling algorithm that is really, really inappropriate for pixel art footage. So part of the point of the building the React RGB scaler site was to take a look at how we could implement custom scaling algorithms using a WebGL canvas. And then fourth and fifth, we have lossy compression. The most ubiquitously supported web video formats only support lossy compression. There are some ways to do lossless, but they tend to only support one or two browsers. And then you also have art designed for CRTs and composite video signals. And the big thing there is that CRTs had two different things going on. One, they have this thing called phosphor decay. So the pixels from previous frames would be blended into the pixels from successive frames. And you kind of just get this general smoothing out of the image as it moves. And then the second thing is that the signals going from consoles to old TVs often used a standard called composite video. You might remember it as the yellow, white, and red cables on an old console. And those signals would blend together nearby pixels because they would multiplex the brightness data on top of the color data. And so they would interfere, and then you'd get this sort of blending effect that's specific to how composite video works. And artists in old video games would actually take advantage of this to create extra gradients. So they would kind of checkerboard with dithering across a bit of color, and then you would go as a gradient from like black to white instead of just going hard. One pixel is black, the next pixel is white. So this allows you to generate way more colors than the console could originally generate. Maybe it can only generate 256 colors, but with dithering, you can multiply that exponentially. And this looks smooth if you play it back on a CRT, but if you capture it perfectly, then it looks like a checkerboard. It doesn't look like the artist intended it. So you have to think about, it's kind of like it's a similar thing in translation with text of formal and dynamic equivalence. And the formal equivalence tries to get exactly what the console would be outputting, and the dynamic equivalence is more like, no, we really want to see what the viewer would have been seeing on a CRT using the console. So this is a highlight. This is one of the biggest things that the RGB scaler site does. It allows you to use custom scaling algorithms against video. And you can see an example here of why that would be really important. So the only algorithm that's widely available in like every browser for upscaling video is the second one, called bilinear. And it takes a linear approach to scaling. Okay, so in your source pixels, let's say you have a green and then you have a brown next to each other. So it's going to be having a little bit of green and a lot of brown, and then more green and less brown as it translates between the source pixels going through the display pixels on your much higher resolution monitor. And on the left, you have something called point scaling, which really does a lot better job for old pixel art, but it kind of has the same problems as the Mercator projection in maps. People love to talk about the Mercator projection distorting the shapes of continents and countries. And the point algorithm really does the same thing. It distorts the shapes of objects with the upshot of getting you really perfectly sharp pixel lines. So for example, if you were to upscale a footage 4.5 times with point scaling, some vertical lines would be 4 pixels wide and some would be 5, and the same horizontally. So as Link moves across the screen, it's not going to be able to say you're 4.5 pixels wide. It's going to be say 4 and then 5 and then 4 and then 5, and you'll get this like wobble and shimmer of the sprite as it moves across the screen. So as a compromise between those two things, what has been happening in the retro video gaming scene has been to use this area effect algorithm. It's been popularized in libretro and then adopted in OBS afterwards. And the area effect, it uses point essentially for any pixels that are entirely covering the area of a source pixel. But if the area of a output pixels covers 2 source pixels, it mixes the 2. And so you get this effect where only the needed to be blended pixels are blended. And this can be done easily in WebGL. And it's done in OBS source code. So part of the project was adopting and translating the OBS area effect from GL on the desktop to WebGL. And here's just a very quick overview. This is kind of what Dragster, the Atari, the famous Atari Dragster 557. This footage is this kind of what this would look like if you were viewing it on YouTube at its original resolution, with all of those different artifacts stacking on top of each other. And then flipping to the next slide, this is the sharpness that you can get if you're scaling with an area effect and coming from a 444 lossless source with all of the color information. So just flipping back and forth a couple times, you can see how treating the footage like that gets you a much sharper and more authentic presentation to the quality of the original footage. Now, there's another effect here, which is CRT simulation. So I mentioned that often the art sometimes wants to be more treated like it was on a CRT. And some of those effects also can be recreated in WebGL. And two of them here represented are scan lines, where horizontal lines are alternatingly painted. And then the second one is that vertical lines are either a red, green, or blue subpixel, and that subpixel is called a slot mask, as you would see on a CRT. That's represented here in the footage as it's scaled up. Instead of scaling up an individual color, we're scaling up the subcomponents of that color. So here's a QR code to the rgbscaler.com site that takes advantage of all of this knowledge and wraps it up into one web player. It uses all those techniques in combination to preserve crisp footage of very low resolution games. We have an area upscaling algorithm implemented on rgbscaler.com, and it's possible by copying each video frame of the video to a canvas element. And I'll walk through some of how that works in JavaScript and WebGL. There's a simulation of CRT effects possible in WebGL 2 as well, like I showed on that previous frame. And the only real requirement for the video input footage is that it has to be, again, be in the original resolution of the console, and that it has to be hosted on a site that accepts cores anonymously. There's some protections in reading video data off to a canvas. And so you have to, if you want to play it on rgbscaler.com, you have to either download it and then play it with a file upload, or you can use it. Well, you can like put a link in the source. You can download the video and play it back by the file upload system, or you can provide a link, and the link can be one of the few test videos available on rgbscaler.com, or as I mentioned, it can be from a site that accepts anonymous cores so that it passes those checks for data security. This works really well for games from the N64 era and earlier, especially the oldest consoles such as the Atari 2600. And because I've implemented this as a NPM library, it's NPM under my name TI-Kevin83 react-RGB scaler. You can easily implement this on your own site, so you don't need to do anonymous cores. You can just pull in the library to your React site, and then you can pass the video URLs in and all the other information you want to do that way. And then this QR code here is a tech demo that should work on both Chrome, desktop, and Android, and in Firefox. So the AV1 video codec is really essential to this, working on the desktop and in the mobile space. It brought in support for 444 full chroma and lossless video footage, whereas in H.264, one of the most ubiquitous formats currently on the web, those modes are not very commonly available. They're only really working in Chrome desktop right now. And this is really important because you can't use anything except the bilinear algorithm in Firefox. You can use the nearest neighbor algorithm using CSS image rendering pixelated, but you can't do that in any other browsers like Chrome, Edge. It only works in Firefox. So this whole library is necessary mainly because that image rendering spec has not been fully implemented by any browsers. Even Firefox's image rendering pixelated system is not following the CSS spec right now. It's supposed to be doing something more like an area effect, and it's actually doing a nearest neighbor upscale. So the AV1 video codec having full support for 444 and lossless footage allows us to then do the scaling on the client side in WebGL and handle the footage appropriately in ways that you otherwise wouldn't be able to do with web browsers. And it's also really efficient because these older retro video games have swaths of exactly identical color, and especially with TASs, as I mentioned, us having the impetus to work on the site for, these are coming out of emulators, so they have perfectly crisp footage. So either if you have like an HDMI modded console and you're capturing that losslessly, or if you're capturing an emulator, those systems are both going to have completely identical swaths of color, and then that compresses efficiently enough that you can actually send lossless footage over the web. H.264 is still more efficient than AV1 in its lossless mode. AV1's really more efficient in lossy modes and more film-oriented things. But lossless H.264, again, isn't like compatible with many browsers, so the fact that AV1 is getting more adoption is really great. So how do you send video to a WebGL texture? Well, MDN has a really great tutorial on that helped me get started, called Animating Textures in WebGL. And that tutorial had to be heavily adjusted for use in React. So just some basic concepts there that ended up working really well was I set a ref attribute on the canvas to a callback, which was defined in a custom hook. And that callback did all of the boilerplate WebGL setup. Things like initializing the textures, initializing the triangles for WebGL to have two triangles to go for a single texture for the video, things like that. Just all the boilerplate to get this working. And then the custom hook has canvas and GL variables stated so that they get updated in the ref callback, and the use hook can use those variables and all its other effects. So things like when you change your browser's width, or if you go into full screen mode, the canvas player's available size is going to change. All those things can be updated in the use effect hooks in this custom hook, and other things like the intensity of those CRT recreation effects, the slot mask and the scan lines. Those can all be done into these use effects in the custom hook, and it really helps clean up and organize all of the stateful interactions of the canvas by having this in a custom hook and then having the ref attribute be a callback that's defined in that custom hook. So how does the WebGL texture handle updating for new frames? There's this really great thing called request animation frame available in the browser, and request animation frame outputs the ID of a request, and then that can be canceled with cancel animation frame. So the video is always pulled for a new frame with this callback, and it just continuously goes through the render loop, drawing the next video to the text image 2D, drawing the triangles, and then setting the next state. And we have to use a set state system because the ID otherwise would get lost between successive renders of the custom hook. Now, I wanted to show a couple essentials of this shader. Like I said, the area effect was ported from OBS source code, and you can see all the links to that in the source of this site. And the source is available directly from going to rgbscaler.com. You can click to view the source, and then you could find the area effect from OBS in there. And the texture is sampled in linear space so that we can say, okay, here you really should go back and be this color from this source pixel, but then, oh, your output pixel is on the boundary of 2, so we can sample you linearly. If you just use the gl.nearest, then there's no way of saying in the shader to be partway where you need the area effect. And this area effect is then combined with the simple effects for the scanline and slot mask. This code is probably horrifying. I'm not really a WebGL expert, but it gets the job done. And what it does is it has a simple way of implementing the scan lines being the alternating blank lines. When you have a CRT, it paints the frames as fields of alternating like this, and then the alternating fields, it's called interlaced. And the way that they would do 240p like video games on the CRTs is they would paint the first field, and then instead of painting the alternate lines, they would just paint directly over the first lines. It would be called double strike, but that would leave empty lines between your pixels. So scan lines helps recreate the fact that it would look like that on a CRT. And the slot mask, again, it blows up the subpixels instead of blowing up the pixels as blocks of perfect color. Another really cool thing about doing this as a library was that in Rollup, I was able to use Rollup plugin string. And instead of having to have my shader code dumped directly into raw strings in the call to gl.shader source, I was able to import them from files named .vert or .fragment, vertex and fragment shader code. And then I was able to get syntax highlighting for GLSL using those things being in separate files. And then I was able to fix up some warnings with some basic declaration files for the IDE. Lastly, to start wrapping up the code demonstration, there's custom controls needed. The HTML5 video player underlying and backing the canvas has to be hidden. Otherwise, you get two video players, and nobody wants to see two videos side by side for no reason. So the regular one's hidden, and the custom one ends up on the canvas. And because of that, all of the native controls of the video, like the play, pause, full screen, all those things are also hidden along with the original video, and the controls have to be re-implemented. But this is pretty easy in React. You can see a basic example here of how the play, pause button is handled, where there's a button and it has an on click to handle play, pause, and then it calls into functions from our custom hook to start the request animation frame loop and play the video, or to cancel the loop with cancel animation frame. Another really, really important thing about this tech demo is that it has to dive into the nitty gritty of the pixels in our original footage. So there's a difference between CSS and device pixels. When you're viewing something on a high DPI display, Windows or other OSs might be saying, oh, your display is really, really high resolution, so we're going to do some effects of scaling in the browser for you. And this is expressed as a device pixel ratio. So a really brief example might be if you're 480 pixels in CSS pixels, you might be 720 pixels in device pixels if you are at a 150% device scaling ratio. So what happens is when we're doing all of our calculation of the sort of amount to scale up the video and the dimensions of the video to use, taking into account the client-side display aspect ratio correction, we also take into account the fact that there's this device pixel ratio and that the pixels on the screen are kind of, you're kind of being lied to almost about how many pixels you have. And you have to get the device pixel ratio to know actually how many you have available on the screen. So the key with all that is the canvas width and the style width have to be set separately. The canvas width is set to the total amount of device pixels that we're going to be rendering, and the style width is set to the amount of CSS pixels that we're going to be rendering. And then just very briefly to show the benefits of this for the amount of data that you're transmitting. If you use a 2D Dragster source like on Atari, this footage is stored at a matter of hundreds of kilobits per second when it's at the original resolution and lossless. So we're looking at numbers like 108 kilobits per second for, or 119 for 8-bit 444 H.264 footage. And like I said, AV1's a little bit less efficient. It can be maybe 200, 300 in this case. And if we look at Super Mario 64, instead of on the order of hundreds, we do have like 5 to 10 megabits per second. But even still, when 4K footage is using 20 to 40 megabits per second these days for online streams, and that's not lossless footage, that's lossy footage, you can get way, way sharper output from these older consoles by storing losslessly at these original resolutions and then rendering them on the client side. So there's some takeaways here. For some reason, H.264 10-bit encoding is a lot more efficient in this lossless mode. So it would be great if browsers had more adoption of H.264's 10-bit mode. But obviously, that's probably not a focus with the advent of AV1. And AV1's really going to be our focus for compatibility. And then second, the file sizes are so small, like I said, that the lossless modes can be really preferable if you have the clean HDMI or RGB modded console, and you can get this crisp capture, or if you're capturing from emulator for something like a tool-assisted speedrun. And then the native resolution lossless encoding is much less efficient on 3D sources like Super Mario 64, but again, the 5 to 10 megabits is still way more efficient than you might get from a full 4K video. So lastly, just a short demo of the site. I'm going to pull up here rgbscaler.com, and I have a couple different test videos. This first test video is some footage from Pokemon Crystal, and if we play this, you can see the whole full sharp pixels being upscaled and on the client side. But a really great example too is its effects for Atari footage. So one of the test footage videos we have is this hero.webm. And you can see here, this is the original resolution of the Atari. It's very squished, but it would end up being a 4:3 aspect ratio on a CRT monitor. So we do our aspect ratio correction client side here by putting in a display aspect ratio. And then when we play the video, now it's stretched to the proper dimensions that it would be on a CRT. And then also we have available the tuning of the slot mask and scanline intensities. So if I pull up the slot mask here, you can start to see how the pixels end up being individual rows of color for red, green, and blue, as if you were blowing up the subpixels and not treating these as individual blocks of color. It might look a little bit dark on your screen, so that's why there's an intensity slider like this, because going for the full effect tends to be very dark on a really high resolution display. And so if you combine that with the scanline effect, you can see the cross hatching in both dimensions, and you get the effect of both the empty lines between pixels and the effect of red, green, and blue being painted separately. So rendering that on the client side helps give you some of those effects that playing on a CRT would have. And rendering in the client side also gives you the ability to scale the aspect ratio with this display aspect ratio setting in a way that preserves the sharpness of pixels. And this is all done in query params, as you can see up here. So because it's all in query params, you can upload one of these videos out somewhere on one of your sites that has anonymous cores, and then you can tune all these settings the way that you think it looks. Oh, that's really close to how it looked on the CRT. Give it the right display aspect ratios, and then you could share this URL. So the proper settings you tuned in would be available for anyone else. So yeah, again, if you want to go to NPM, this is Ty-Kevin83 React RGB scaler out on NPM. And you can see here the availability of this public component. You can use this on any of your own sites. Thank you so much for watching the demo. The TaskBot team is available on discord.task.bot for anyone who has more questions or who wants to get into this sort of development scene. And I appreciate your time so much.